upload it soon. So these slides are up if you want to fetch them, and the R Markdown file is up as well. Okay, so today what we're going to cover are two additional types of GLM. We're going to cover models that are very well suited for count outcomes, the Poisson regression, and we're also going to cover models that are well suited for categorical outcomes, the multinomial regression. And these are discussed in the book as well. There's one type of GLM that's covered in chapter 11 that we're not going to get to, and that's survival models. I encourage you to check that out, because survival models can be incredibly useful. If you're ever dealing with an outcome that is about the time to a particular event, like maybe you want to know the time it takes someone to graduate, or the example of the book is the time it takes a cat to be adopted. Often these are used in exactly what it sounds like, survival, right? How long does a patient survive after being exposed to some particular disease? Now, the problem with these models is that sometimes, so we observe the time to an event, right? The problem with these models is that a lot of times we don't observe the event occurring within the time that we have observed. And so what's called censorship is a big problem in these models. And so there's very clever ways that we can address censorship and still obtain accurate estimates of the time to the event. So we're not going to do survival models. They're super useful, though. So I do encourage you to check out that part of the book. The second edition of the book is out, and I've got a copy on the way. So if you want to check out the final second edition, it is available now if you have $100 lying around, which I'm guessing a lot of us may not at this moment. And that's Iris saying hello if you heard her. Okay, here we go. So, oh, here's the baby. Hey, baby, come say hi. Here's Iris. Iris wants to teach stats.
Hello, baby.
Okay, Iris. Okay, so we're going to go back to GLMs real quick. So GLMs, remember that we've got a few components, right? And these look really similar to what we've been working with in the past. So we have the likelihood of the data, which is the kind of small world data generator, right? The thing that we think produces the outcome that we're interested in. So one example of the likelihood we worked with last week was the binomial likelihood. So that's here. We can say that Y is distributed binomial with two parameters N and P, right? In the case of the binomial likelihood, N is the number of trials, and P is the probability of the outcome being equal to 1 or true, right? Probability of success is often how that's described. So our likelihood is the statistical model that we use to describe the distribution. Bye, she's bored. What we're doing. Bye-bye. Yeah, I gotta go. You can go find mom. No? Okay, you want to stay with me for a little bit? That's okay. Okay, babies are indecisive. So yeah, the likelihood describes the statistical distribution of our outcome, right? And remember, that's conditional on our predictors, right? Because what we're going to do next is we're going to provide a linear function that provides us a linear combination of parameters and variables that give us a parameter of our model, right? So the data is distributed binomial, conditional on the value of N and P, right? And in this case, P depends on some parameters and depends on some data. No? Going by or not? You can't decide. Okay, she's back again. There we go. Okay, so in the case of the GLM, right? Yeah, in the case of the GLM, so the normal model does not require, it's already on a linear scale, right? Mu is linear. But on the case of the GLM, we have some additional bounds on our model, right? So for the logistic regression, we need to be able to have our outcome on the probability scale, right? P is a probability. Do you want me to close the door? Okay. Can you say bye-bye? Bye-bye. Okay, I got to wave. So I guess we're good. So P is on a scale of 0 to 1, right? And so we need some function that will bound our line, which theoretically ranges from -infinity to positive infinity. We need some function that will rescale that onto 0, 1, right? And so we use what's called a link function, which converts our likelihood parameter to a linear combination of predictors, right? So it converts, in this case, P, which is bounded between 0 and 1, to a unbounded real number scale, right? Minus infinity to positive infinity, right? And so there's a lot of different link functions we can use that do this similar, that provide this similar phenomenon. We'll see another today. Actually, we'll see a couple today. So our model, right, has the likelihood, and that's what our distribution of our outcome is. It has our linear function, and in the case of GLMs, a link function, and it also has priors, right? But that's all we need for our model. So we need our likelihood, our linear function, and our priors, right? And so this is really similar to what we've been doing all semester, and this is review, right? But the thing we've done is we've switched out our likelihood function from the normal to some other likelihood function, and we've added this link function onto our linear predictor, right? So effectively, right, we could rewrite the linear predictor here. We have it written as logit p equals alpha plus beta x. We could write it as p equals logit inverse alpha plus beta x, which the logit inverse is also known as the logistic function. So we could write it p equals logistic alpha plus beta x, and that's equivalent. Okay. And what we're going to get into today, we're going to use the natural logarithm of the link function. And so we'll have log of a parameter is equal to alpha plus beta x. And the inverse of that is that the parameter will be equal to e to the alpha plus beta x. Okay, so let's go. So the binomial count model, which we covered briefly last time, is a generalization. So we typically use the binomial model, or a lot of what we've seen with the binomial model will have been cases where we have n equal to 1, and we're treating the binomial as a special case, which is the Bernoulli, right, where n is fixed at 1, and that's logistic regression, right, when we're saying we have a binomial model with a fixed n of one trial and a probability of outcome p, but there's no reason n must be fixed at 1, right? We could use the binomial model to generate counts of events with fixed probability p, right? Probability p conditional on our predictors and our parameters, right? But we have another special case of the binomial. So the Bernoulli is one special case of the binomial when n is 1. But today we're going to focus on another special case. So the expected value for a binomial variable with probability p and number of trials n is np, right? And the variance is np times 1 minus p. Now, what happens when n is very large and p is very small, right? So if we have a lot of trials and we have, and we got a p that's very small, so the event is rare, then np and np times 1 minus p are approximately equal to each other, right? And this is another special binomial. This is called the Poisson, right? The Poisson is the special case of the binomial where the expected value n times p is approximately equal to the variance, right? So the Poisson distribution has a special feature where it has a single parameter and it describes both the mean and the variance of the data. So we're going to take a look at this. So the Poisson likelihood is a very useful distribution for modeling counts, right? Which we could also describe as non-negative integers, right? So it's bounded between 0 and positive infinity, but each, it's a discrete distribution where it only takes on integer values. So 0, 1, 2, 3, and we'll see what this looks like in a second. We can describe a variable as Poisson distributed with, y is distributed Poisson, and we typically refer to the parameter of the Poisson distribution as lambda, right? So this is lambda. We're going to see a bunch of it today. Okay, so the expected value of y, also we can describe it as y bar, is equal to lambda, right? But in the Poisson, the variance of y is also equal to lambda, right? So as the expected value increases, the variance also increases. And this is something we really commonly see with count variables, right? As the expected count increases, the spread around that count also increases, right? So if our expected value is 1, we might have a really low variance around it. But if our expected value is 1,000, we might have a really high variance around it. Here's what this looks like in practice. Oops, apologies that this kind of cut off. So we have here a Poisson variable with an expected value of 1 on the top left panel, right? We can see that we observe a lot of zeros. Yeah. Sorry, did someone have a question? No? Okay. So we have a lot of zeros here. This spike, these are densities, right? So what I've done is I've simulated out 10,000 draws from a random Poisson distribution. You can check the R Markdown file if you want to see the code behind this. I hid one chunk of code that did this. But what I have here is a spike at 0, a spike at 1, and then we have a decreasing number of counts after that, right? But unlike the normal that's symmetric on both sides, right, this is skewed. And it'll be skewed until we get to relatively large values of lambda. So this is when lambda equals 1. This is what a Poisson looks like, right? We observe a lot of zeros, a lot of ones, a fair amount of twos, not as many threes, very small number of fours, a very small number of fives, and non-zero numbers of 6, 7, 8, 9, 10, 11, 12, but very, very rare, right? Okay, 2, similar, right? But now we see that the sort of peak of the distribution moves away from 0. 3 moves further away from 0. 4 moves further away from 0. But we can see the spread of the distribution getting wider as lambda increases, right? Not only is the center of the distribution moving, but the shape of the distribution is flattening, right? Those peaks are going down and the tails are spreading out to the point that we get to 9, and you can't really see it very well, but it's quite spread out. And when lambda gets large, right, when lambda is equal to, let's say, 10, 11, 12, it is approximately symmetric, right? So once we get far away from 0, it's no longer skewed, right, because it's not bunched up at 0. What the Poisson does is it bunches up a lot of density closer to 0, right? And so that tail at 0 kind of soaks up all the variance that we'd see on the other side going positive, because nothing below 0 is allowed in this distribution. But we see here, right, there's nothing that's not an integer in this distribution. It produces only integers, right? So 0, 1, 2, 3, 4. No decimals. And this is great when our outcome is a count, right? This is perfect when we're looking at event counts. The other thing that's nice about this, right, is it has this built-in mean variance relationship where we see higher levels of expected variance for larger counts, right? So like if I'm comparing, and we're going to do this in a moment, the expected number of events of, I don't know, how many food trucks there were in a city on a given day in New York City versus in, I don't know, Dayton, Ohio, right? The expected number in New York will be higher, but the variance will also be higher versus Dayton. We might have a lower number, but we're more certain about where that number is going to be, right? Have lower variance on it. Okay, so let's look at each Poisson variable a little more closely, just so I can kind of drive home this mean variance relationship, right? So if I take this Poisson demo I made, which has values of lambda from 1 to 9, we see that the mean and variance are approximately equal to each other, right? That as the expected value goes up, right? And the expected value is equal to lambda, right? So for a Poisson 3, right, the average count is going to be 3. And the average variance is going to be 2.94, right? A Poisson 8 is going to have an expected value of 8 with an expected variance of 8. Yeah, and if I increase the number of simulations up to 1 million, it would converge to those numbers. Yep. Questions about that? This is just kind of basically how the Poisson behaves. No? Okay, cool. So as a GLM, here's what we're going to do. It's a really useful GLM. So for any non-negative integer y, we'll treat y as a Poisson distributed variable with single parameter lambda. And we're going to use the log link function, right? If you look at the likelihood function for the Poisson, there's an exponent in there. So taking the logarithm of it converts it onto a scale that we have a linear shape on, right? So taking the logarithm of lambda converts us into that linear space, right? And vice versa, exponentiating the right-hand side of the equation gets us onto a lambda space. So the logarithm is our link function here. So the log of lambda equals alpha plus beta x, right? And we'll use appropriate priors for beta and x. I'm not showing those here, but this is our GLM, right? Our GLM is now that y takes on a Poisson distribution, and our log is our link function. And this does implicitly mean that the relationship between predictors is now multiplicative, right? Because if you remember your rules of logs and exponents, right? And we'll see this in a moment, right? If we have e to the alpha plus beta x, that is equivalent to e to the alpha times e to the beta x, right? So we get a multiplicative relationship between parameters now rather than an additive relationship. And that might have some consequences for how we specify models. We're not going to go into too much detail on that today, but it's something to keep in mind. And another reason I keep kind of driving home visualizing your inferences is key. This is another reason why visualizing your inferences is key, because the parameters may not mean exactly what you think they mean anymore. Okay. We're going to use some data from a paper of mine on police killings in U.S. counties. And here, apologies to Asan and Sophia who have seen this material before. A lot of this is stuff that we covered last year in intermediate, but we'll kind of obviously apply the Bayesian approach. Okay, so we're going to read in this data. It's in the slides folder if you want to follow along. So you can run this line of code to read in the data. If you've done a poll, it's in there now. FE demo. And so what we have here is a reduced form version of the data I used for the paper, where we have a FIPS code, which is a county identifier. We have a state identifier. We have the population in that county for a particular racial or ethnic group. And we have the number of deaths that involved police over about a 5-year period or 6-year period. So what we have here is a county by race table of number of deaths coupled with population data. So this is what we're going to use to build out count models. Now, deaths is a discrete outcome, right? If we're talking about the number of deaths in a county over time, we can't have 1.3, right? We're going to have a discrete count of events, and this is precisely the kind of outcome that Poisson models are well suited to. So we're going to define a Poisson regression of deaths. I apologize, it's not death rates yet. We're going to get to death rates in a moment. Of deaths D. So we're going to say the deaths in county I for racial or ethnic group, right? For a particular racial and ethnic group are follow a Poisson distribution, right? With parameter lambda, the logarithm of lambda is going to be equal to a race-specific intercept, right? So we're going to estimate. We here have these are men's deaths only. We're going to look at an intercept for Latinos, an intercept for whites, and an intercept for African Americans. And we're going to allow that intercept to be normally distributed 0, 2. That's a pretty vague parameter, vague specification. Because we're on the logarithmic scale, right, we need to think about, okay, so what's e to the minus 2, right? What's e to the 4, right? These are what's e to the minus 4. These are the kinds of outcomes we'll be thinking about. So you may want to explore it on the scale of the inverse length function to get a sense of where that parameter ought to live relative to what you think it's going to be, right? So for example, right, if we think there's a death rate of, so this is going to give us relatively flat, vague parameters. E to the minus 4 is 0.018 deaths, right? E to the 4 is 54 deaths. So we have priors that basically include 0 and go up to 55, right? So those are pretty vague, and that's going to capture just about all U.S. counties. We could go vaguer if we wished, right? A normal 0.4 would allow us to have, more mass close to 0 and as many as 3,000 deaths in a county, right? Which we don't observe anywhere. Okay, so, but that's pretty vague. Oh, we don't need a sigma prior here. What am I doing? Sorry. You can tell that these slides have not been edited as much as I might have liked. Most of my prep is happening after kids go to bed. Sorry about that. I'll clean these up before I repost them. Okay. Told you to be patient with me. That's what I meant. Sorry about the errors. Okay, here's how we estimate the model. Similar to what we did last week. McElrath really encourages us to convert things to integers when we use factor variables, and factors work fine. His problem with that comes with the labels on factors, I suppose, getting mixed up once in a while, but I haven't seen any issues with that. So I'm not going to do it. I'm going to keep things as factors, because what a factor implicitly is it's a character label and an integer underneath it, right? So in this case, when I run factor race ethnicity, what it's going to do is it's going to take the first value it hits in the data. It's actually going to alphabetize them. And so in this case, black will become 1, Latino will become 2, and white will become 3 when I apply factor over it. So it'll still preserve those labels, though, so it can then work on a numeric scale or a character scale, and that's a nice behavior for what we're going to want to do later. Notice here that I add 1 to the population when I take the logarithm of it. We can't take a log of 0, right? And there are some places, some counties that record 0 Latino population. So I add 1 just to ensure that I don't end up with, an error when I take the logarithm. Okay, so I'm going to select those 3 variables. I'm not going to use log pop yet, but I'm going to use it later. Here's my model, right? Same as we've done before. And now I actually do specify it correctly without unnecessary priors, right? Okay, so deaths follows a Poisson distribution. Deaths is just the raw count, right? So here we saw a bunch of zeros. But later there are counties that are definitely non-zero. So we're going to define deaths as Poisson. We're going to use the log link function on L, which is our lambda parameter. We're going to specify an intercept for each racial and ethnic group. And we're going to say that those intercepts have a prior distribution that's normal 0, 2, right? Just to allow for, pretty vague locations for where those intercept terms are going to end up. I'm going to estimate it using MC with Ulam, right? 4 chains, 2 cores. So here's our convergence trace plot. Looks pretty good, right? The chains are all kind of covering similar territory and appear to be mixing pretty well. So I don't have any concerns about convergence based on this trace plot. Here, oh, right, I didn't do depth too. Okay, well, they're hard to interpret. I'll switch you over to, no, I won't. But just trust me, they're hard to interpret. I'll show you some later. What you get, right, is things on the, so here we can see the values of alpha 1, right, range from like minus 6.5 to minus 0.5. And that's the alpha for African Americans. The alpha for Latinos ranges between minus 0.9 and minus 1.1. And the alpha for whites ranges between 0.02 and minus 0.12. Now, what the heck does that mean? Right? Those are our posterior ranges. And this gives us a kind of, bird's eye of the posterior density. What the heck does any of that mean? Right? It's on the logarithmic scale, so we have to exponentiate it to turn it into expected death counts. Now, we know that negative values on the logarithmic scale are underneath 1, right? Positive values are over 1. But that's about it. It's hard to interpret on this scale. So if I wanted to look at these parameters alone, I would need to exponentiate them first. Right, so I could exponentiate these posteriors to convert them onto the count scale. But typically, especially if we have a complex model, it's easier just to directly work on the scale of the outcome using link, right, or sim. That's what I'm going to do here. Actually, in this case, I'm just going to extract samples, right? And I'm going to turn those into a data frame. I showed you pivot longer in lab. I'm going to use it here, right? And then I'm going to apply the inverse link function, which is the exponentiation with a mutate, right? So here's where I apply the inverse link. Now, if I just use link, it would have done that for me, right? The reason I have to do it here manually is because I used to extract samples just because I wanted to kind of show my work on this. But link would do the same thing, and we'll use link later. Not the director. Okay,
Well,
so yeah.
I have a question. Why did you use pivot longer?
Okay, so because what I wanted to do is stack them on top of each other with the name of the racial and ethnic group on it. So if you work through this on your machine, what you'll see is ordinarily what extract samples does in this case is I have 3 scenarios. I have 3 parameters: alpha for African Americans, alpha for Latinos, alpha for whites, right? And I'm going to rename those columns. I'm going to turn it into a data frame. I'm going to rename those columns to match the factor labels. Then I have 3 columns: black, Latino, white, right? And what I want is I want 2 columns. I want 1 column for race and 1 column for posterior parameter estimate, so I can ggplot the densities nicely, right? And so that's why I use pivot longer, is to basically put the variables in columns and remove the variable from the column name, right? The variable race is in a column name right now, but I want it to be in its own column. So basically, I take those column names and I put them in race ethnicity, and I move the values to log lambda.
Would you have had to do that if it wasn't a factor? If it was,
Yeah, that's what the apply stuff we've been doing implicitly does.
okay.
Yeah, because what we do is we take that apply and then we move a row into a column. We're
Hmm.
we're effectively, and we typically reduce it when we're on a continuous scale, right? We reduce it usually to 3 columns. We reduce it to like the MAP, the mean, and the lower and the upper bound. But
Hmm. Yeah,
we're
yeah, yeah.
pivoting that from wide to long when we do that.
Okay, cool. Thank you.
Yeah. But when we're in factor territory, just doing it this way, once you get at your head around kind of moving from wide to long, this is the equivalent thing to do. No reason I
Uh,
couldn't have said take this row and make it a column, right? With a mutate, as I've done before.
Hmm.
I just use pivot longer instead.
Cool. Thanks.
Yeah.
Quick question.
Yeah.
So you said you're using link instead of extract samples, but that's not the linking that we've done for the models, but the actual link function
I,
on R that connects the model to the data, and it does the same thing as the extract samples, basically.
so extract samples does some work for us. No, I'm sorry. Link does the link function, not the GLM link function. Link parentheses, right? The rethinking R function link does some work for us. What it does is it applies the linear function to the simulated data we've provided, and it applies the inverse link function. So if we use the link here, it would give us the the posterior parameter estimates on the scale of the outcome, which is a count, right? So what I've done here is I've just extracted the samples on their original scale, which is on the log scale, right? But to get them on the expected death scale, I do the extra step here of exponentiating them. You don't need to do this if you use link. Link does 2 things. It applies the linear function and it applies the inverse link function. So you get it on the scale of the outcome automatically.
What's the value of keeping it on the linked function, like the exponential, the log value?
Uh, in this case, none. I'm inversing it anyway. I just kind of wanted to show you how the link function works. So pedagogical.
All right, thank you.
Yep. Yeah. No, sometimes we want it on that scale if we're, really want to look at just the distribution of the parameters themselves, right? We may want it on the original scale. But most of the time we want to work, if we're talking about the outcome, then we want to work on the scale of the outcome. So now I'm going to ggplot it, right? And here is what we see, and it's kind of surprising, right? The blue is the value for expected white deaths. Green is the value for expected Latino deaths, and the red is the value for expected Black deaths. So what this can be interpreted as is this is the expected number of police-involved killings in an average U.S. county by race ethnicity, right? And so this model is showing that there are more expected white deaths due to law enforcement than there are expected Black deaths than there are expected Latino deaths. Anyone have a sense of what might be going on here?
Well, if it's just number of deaths and it's not a relation to the population of the county, then it could just be a reflection of the fact that there's more white people.
Correct, right? The average U.S. county is pretty white, and the U.S. population is like 56% white, something like that, right? About 12, 13% African American, and I forget, I think 18, 19% Latino. I forget off the top of my head exactly the right numbers. But yeah, there's more white people, so there's more chances for white people to be killed by police, right? Because the population is larger. We haven't done anything to adjust for the composition of counties, to adjust for how many people there are, right? All we've said is what's the expected number of deaths, right? And so this gives us the expected number of deaths in the average county. We haven't scaled, and most counties are quite small, right? The 90 some percent of the US population is in like 300 counties, but there are 3,300 counties in the United States, right? So 3,000 counties with really small populations. Okay, so the expected number of deaths is like 1, right? Over this 6-year period. But that includes New York, where the actual observed number of deaths is like 200 something, right? And it includes, my favorite, Ossaga County, Alabama, which is, the first county we always see. It's that first FIPS code right there, 1001, right, where there were no recorded deaths in the data. So, yeah. Okay, questions on basic count model, right? So we can see that this is, this is our lambda parameter for each of them, right? We get 3 lambdas. We get a black lambda, a white lambda, a Latino lambda. You can see that the peak on the Latino lambda is closest to 0, so that peak is highest, right? We can see that because remember that the mean variance relationship of the Poisson means we get more spread as we go further away from 0, right? So here, our expected value is pretty close to 0, right? And remember, this is on the average count scale, right? If we were to simulate directly from the Poisson using this lambda, we would get integers, right? We would get zeros. In the case of Latinos, we would get a lot of zeros and a few ones, and very small number of 2s and 3s, right? For blacks, we would see, a lot of zeros, a lot of 1s, small number 2, small number 3, small number 4s. For whites, we would see fewer zeros, right? Here we're getting close to that, Poisson with the lambda equal to 1. So we're getting close with whites to this distribution on the count scale, right? This is the distribution of the expected values, right? So this is our posterior inference for where lambda is for each group. Any questions on that? We're good? Okay. So, this, as Sophia pointed out, this model is obviously not great because it just tells us about the expected number of deaths. It doesn't tell us about the expected rate of death, right? We may not be interested in just in how many people die. We may be interested in what proportion of people are being killed in particular populations, right? How common it is relative to the size of the population. Okay, so the standard Poisson model is unbounded, right? It assumes that each observation is drawn from a similar unit. So in this case, we assume that each county had about as many chances for Latinos to be killed by the police as it had for African Americans to be killed by the police as it had for whites to be killed by the police. If we're treating this in a kind of causal inference way, right? If we're treating it in just to like predict how many deaths are going to occur, then this is fine, right? But if we're treating it in a like, what's the relationship between race and police violence way, then this isn't great, right? Because we know that each observation is not drawn from a similar unit, right? The population sizes are very different. But with a really convenient and easy to use trick, we can use Poisson models to estimate event rates using... Yes?
I have ballerina tea party and a dance party today.
Did you hear that, everyone? Dorothy has a ballerina tea party and a dance party today.
It's so exciting.
So exciting. So exciting. I'm very...
I wish I could go. Oh, Monique!
You can, in your mind, in your imagination. We can all have our own ballerina tea party. Okay. So, homeschooling is awesome. Let me tell y'all. Yeah, she's a delight most of the time. Anyway, okay. So back to regression models. So the standard Poisson model is unbounded, meaning that count can go up to infinity, right? It assumes that there's nothing constraining the right-hand side of the count model other than the lambda parameter, right? But what if the scale, what if it's bounded, right? There's a maximum number of events that could occur because maybe an event can only occur once per person, right? And like a death can only occur once per person. So maybe there's a maximum number of events that could occur. Or maybe there's a different exposure for each, right? The book uses the example of time, right? And so it uses the example of like a factory's productivity, right? And what if we have one factory that produces 40 widgets per week and another factory where we get data that it produces 20 widgets per day, right? And these are on very different scales, right? We have a week scale and a day scale. So can we compare those using a regression model? And we can. What we can do is we can use what's called an offset term. This is also called an exposure term. So McElrath calls it an exposure term. And I think that intuitively makes sense, right? How much exposure is there to the event in the population of interest, right? how often could the event occur. But in R, you'll often see that's called an offset term. And so if we have different units that we're drawing from that have a different exposure, right? Meaning, in this case, a different population size. It could be a different exposure in terms of the amount of time that a unit was exposed to the conditions that would produce the outcome. Could be a lot of different things. But it's going to be effectively, we can convert our model away from account into account per unit exposure, account per unit offset, right? So in this case, we're going to turn it into account per unit of population. But it could be account per unit time. It could be account per unit, you can imagine, for an offset or an exposure. So it scales lambda to the size of the exposure, right? And it turns into a rate. And this is great because, there's no reason we can't use a normal model for rates, but remember that the Poisson has this really nice feature that the normal does not, where it's bounded at 0, right? And we know that event rates can't go negative most of the time, right? So event rates are bounded at 0. And so we often want this skewed distribution clumped at 0 when we're modeling event rates. And the Poisson is great for that. Okay, so how do we work with an offset? It's pretty easy. In base R, if you're using just the GLM function, there is a term for offset. You just say offset equals log of your offset, right? But in the ULAM and the QUAP models we're using, we're not going to do it directly. We're actually going to incorporate it directly into the model. And this is something that we can apply pretty broadly. And it also makes the math of how it works a lot clearer. So here's how it works. So let's estimate a model that includes population P as an exposure variable. Right? So again, this could be anything. It could be time, population, or any other measure of event opportunity. Right? Think of this as the opportunity, time that, or the opportunity for the event to occur. So obviously, if we're talking about police deaths, the opportunity is the population size. If we had a better opportunity variable, like maybe police stops, or some kind of police civilian contact rate, that would also be acceptable here. But then we might want to think about any bias that would induce if race or ethnicity is correlated with police contact, which it very much is, right? So we could get into some weird kind of correlation structures there. But nonetheless, and this is a debate that's going on in the policing literature pretty heavily right now, is kind of what's the correct exposure variable to use. And I'm a firm advocate of using population as an exposure, because race and policing are really tightly bound up together. Okay, anyway, we're going to use the same likelihood. Deaths are distributed Poisson lambda, right? But we're going to mess with lambda a little bit. Instead of using our typical lambda, McElrath parameterizes this with a mu in the book just to keep his Greek straight, and I think that's wise. Here I'm just going to keep using lambda and p for ease, so I'm not putting more Greek on the screen. But effectively, we're going to turn that lambda into lambda, right? So we get Poisson lambda, but on our likelihood function, we're going to add this p parameter. So we're going to say on our look that the logarithm of lambda over p is now equal to alpha plus beta xi. So this is now our left-hand side of the equation, and this is our right-hand side of the equation. But remember the rules of log, that the log lambda over log p is equal to log lambda minus log p, right? And once we have that, we can really easily rewrite this as log lambda equals log p plus alpha plus beta xi, right? So lambda can stay the same. The only thing we're going to do is we're going to add the logarithm of the population size, or the logarithm of our exposure, to the right-hand side of the model. But note that we don't have a parameter attached to it, right? So there's nothing from the data that nothing from the model, nothing the model needs to estimate in terms of any uncertainty around a coefficient on that parameter, right? It doesn't have a beta on it. It's just log p. It's not a predictor, right? It's not a predictor. What it's going to do is it's going to scale the model to the offset size, right? So what it's going to do in this case is, for those places with larger populations, we have a larger expected count, right? and that's by log p. So it's effectively an order of magnitude. If your population is an order of magnitude higher, then your expected count is an order of magnitude higher. But it's a really convenient way to allow New York City to have a much higher expected count of deaths than Autauga County, Alabama, right? Because we're just going to add the log population size onto it. Okay, so here's how it looks. Any questions about the math on this? No? Okay. Working with logs may be something that you're not especially comfortable with. That's okay. It turns out this is actually really easy to model. All we do is this, right? This is our model, same as before, but note I've added the log p. That's the only difference. And it's not a predictor, right? It's an offset. It doesn't get a parameter. We could add it as a predictor with a beta term if we wanted to, but then we're kind of like letting population size dynamically predict counts of deaths. What this implicitly does is says, no, the beta for log, the implicit thing we're multiplying log p by here is 1, right? It's fixed at 1. We're not allowing the model to let that vary at all. We're saying it's always going to be 1. And that's how to guarantee that you get that offset relationship so it's interpretable as a rate. And that's something desirable here. Okay, so here's how we estimate the model. All I did was add log pop into the equation, right? But then notice it's not B times anything, A times anything. It's just log pop. Okay, so it's pretty simple to estimate. That's exactly the same as the prior model I ran. I only added log pop into it. Same exact thing. Thinking back to the Titanic example, if you all worked that for homework this week, right? We could have done a count of deaths. We could have converted that into a count of deaths by cabin or something like that. And we could have used like the number of passengers in the cabin as a rate, as an offset variable, right? We could have like constructed a column that's like total number of deaths, total number of passengers, and then used the number of passengers as an offset for the count of the number of deaths. Yeah? Which is going to be really similar to what we did with the binomial model. And it would be equivalent, it would yield you very similar inferences to what your logistic regression yielded. Okay. So let's interpret the model and check convergence diagnostics. This time I remembered to add depth to it, so I can talk to you about these parameter estimates now. Okay, minus 9, 8.9, minus 9.6, minus 10.1. Remember that 1 is black, 2 is Latino, 3 is white. What the heck does that mean? What does minus 9 in this scale mean? Now, if you actually did want to look it up, right, what you could do is you could go to R, and that's what I'm doing right now, is I'm typing exp minus 8.9. And it returns 0.0001, right? What is that? Anyone got a sense?
That would be.
Go ahead.
0.0.
Lorena, go ahead.
What?
So what that is, it's the log expected deaths per person. Right. So in this case, when I take the exponentiation, when I take e to the negative 8.9, I get that 0.001. I'm sorry, 0.0001. That means for every person, we expect 0.0001 deaths. Right. Now that's a funky scale. Right. So if I want to get this onto a scale that we tend to work with in like epidemiology, I might want to look at it in terms of deaths per 1,000 or deaths per 100,000. So if I multiply that by 1E5 to get it onto 100,000, I get 13.6 deaths, right? And so that's for every 100,000 African Americans in a county, I expect 13.6 deaths, right?
Wait, so did it change to per person because of just adding the offset?
Because of adding the offset, it changed to per person.
Okay.
Yep, that's exactly right. So the offset term converts it into a rate, right? Remember that now we've defined it as the logarithm of lambda over p. And lambda is our count, expected count, and p is our population. So now this is expected deaths per population. Now my -9 on the log scale is really small, right? But if we're working on it on a per 100,000, all we got to do is multiply that out by 100,000 to get it back onto another scale. So to compare, right, we have -8.9, and that converts to 13.6, and let's just run it on this one, minus 10.1607, and I'm going to multiply that by 1E5, and that's 3.8. Right, so we expect for 100,000 African Americans in a county, we expect 13.6 deaths. For 100,000 whites in a county, we expect 3.8 deaths.
So should we, my question is, because obviously you would want it in that scale rather than per person, would you manipulate the priors to get it into that scale, or would you manipulate your extract samples to get it in that scale?
Do anything, right? So I'll show you what I'll do. I'll show you what I'll do in a second to interpret it. But on the you notice the prior is exactly the same as it was, right? 0, 2, which actually the posterior ended up being really far away from that in this case. Like -9 is really unlikely under a prior alpha 0, 2. I have a lot of data here, so the data is going to overwhelm that prior. So I might want to go with a prior that's further away from 0, like a prior that's like -4 or something. I actually have, in the paper, we had priors on death rates that we used that were based on some older epidemiological research that did put the prior kind of at like 1 per 100,000 was our prior for death rates. So that's equivalent to whatever, the log of 0.0001 is. But yeah. So
Okay.
that's what. So your priors aren't doing that. What's doing that is log pop. Now you're asking how I get it on the 100,000 scale.
Well, I guess I'm just emphasizing that. So if we did this for the homework, right?
Yeah.
We made the offset like per cabin, then we'd have to think about what our outcomes are in relation to the units.
Sort of.
Analysis.
Yeah, I mean, if your data's on a count scale, right, and you're thinking about like deaths per ticket or something, right, deaths per passengers in whatever subgroup, then you don't actually need to change very much if you transform the data appropriately from the from like the unbounded count model. If we're already estimating the unbounded count model here, right, then the only thing we've changed is adding in the offset term there. That's the only change. Now, from going from the binomial model to the count model, that is a substantial change, and your priors would be different in that context, because the scale is now a count and not a 0-1 probability. Does that answer your question?
Yeah.
Okay, cool. Now to get to the deaths per 100, so my outcome is now on the deaths per person scale, and that's why my parameter estimates here are like -9, and remember here they were 0. They were like -0.55 for African American, or so that the maximum here was like -0.57 for Latinos. It was -1 for whites. It was close to 0, right? And now we're at like -9, -10, right? So we've really pulled those estimates further away from 0 because we're offsetting by population, right? So those numbers are really, really small. If I wanted it to have it on the deaths per 100,000 scale, I could go ahead and scale population to the 100,000 units, and it would give it to me on that scale. We can scale this however we want. But here's what I'll do, right? Here's the data. Here's the regression outcomes. Again, all this is to say, this is a simple model, so I can just exponentiate those and interpret them. But if you have more complicated models, basically, anytime we have a beta in there, an additive beta in there, it's a multiplicative relationship, and it gets harder to interpret. So we're going to visualize it, right, as we typically do. The main reason I want to look at this output is to look at ineffective and R hat. And in this case, R hat is close to 1. Ineffective is, close to 2,000. I didn't get any convergence warnings on it. And if I look at the trace plot, it looks fine. So I'm not worried about the validity of these estimates. I think the sampler did its job. That's most of the time when I'm looking at the parameter estimates, that's what I'm looking for, is just to check convergence. And then I'm going to move on to interpretation with visuals.
I'm sorry, I have one more question.
Yeah.
So the beta you're referring to in this instance is the offset. So because we added the offset,
No, sorry. No.
Okay.
There's no beta on the offset, right?
Okay.
The beta is if I had a linear additive predictor. right?
Okay.
If I had a like, maybe I think the relationship depends on police force size or something like that, right? I could add a beta for the number of officers per capita or something like that as a linear predictor. But then, e to the alpha plus beta x. So if alpha is the race intercept and beta x is officers per capita, then it's not alpha plus beta x strictly speaking on the outcome scale. Then it becomes e to the alpha times e to the beta x on the outcome scale, right? So we effectively get an interaction, but you need to visualize it to really get what's going on. That's
Frank, I have a quick
Yeah.
question.
Yeah.
Would there ever be an occasion where we would need to do two offsets in one model? Say, like you had two betas, or because you're always going to be working with one population, right? So maybe
I don't know.
Yeah. Okay.
I've never encountered that, and you could if you wanted to like do like per population per time.
Right. I guess.
And I could just make my single, so I could do like log lambda over p over t, right? But reduce p over t.
Right.
So
that's probably in
this paper we did that, right? Because I wanted to convert the death rates. Right now they're deaths per person per 6 years because I have a 6-year window on the data. So we did end up converting it using a conversion of the number of days. We converted our 6-year scale into a 1-year scale, right?
Okay.
We actually because we had like 6.37 years or something because we just pulled the most recent data available to run the models, and those were not exact years, and so we had to convert that onto an annual time scale.
Right.
I didn't put that in the model. I just ran the model with the sum of the population over those full 6 years. Then converted it into a time scale later.
Okay.
So the answer is yes, but I don't think you need to put it in the model.
Okay.
I mean, you can do unit conversion all day long, right? The thing that we're doing here is we're dramatically rescaling the posteriors for our regression parameters. Okay.
So, quick question on that. What's the value of doing it within the model versus just scaling the data per population?
Yeah, I just was thinking about that. It's a good question. I would need to do a little homework to kind of fully think through the answer to it. Because, in theory, we could divide these by average population size and convert. So this is just our unbounded counts and convert those. I think what's going to happen is the compression towards zero might differ a little bit on the shape of the curve. I don't know exactly, is the answer. It's a convenient feature of the model that I've always just done.
Because in the past, that's what we've done. We've just normalized it to the population size to get a proportion.
Yeah, I mean, the shape of the curve is going to look a little different based on how clumped up it is towards zero on a rate scale versus on a count scale here. So I think we will actually get slightly different inferences, but I would need to think about that.
Yeah.
Is there an advantage? Do you feel like this representation is more accurate than the alternative of dividing?
I feel like this representation is more accurate. This is rates. I think, I think you would, Sophia, you were going to chime in?
Yeah, that was sort of what I was trying to get at when I was asking about when you would put the scales, like if you'd put the scales in the model versus.
Just convert it later.
But yeah, and then so my other question is if the GLM, like a linear model, is problematic because it goes infinitely, couldn't we just set a prior that it starts at zero? And like, what's the benefit of? Yeah.
The Poisson versus using a some prior that's going to constrain it to be positive, or using a log normal is sometimes what people do, or using a gamma. There's lots of choices you can make. Given that our outcome is a count, the Poisson is the maximum entropy distribution for a count, because those gamma, now given that we're working on the rate scale, so these are all modeling choices. There's no exact answer to a lot of these questions, right? Some of it, in the case of count outcomes, you can use the maximum entropy standard to make a call that, a count model is better than a continuous model. And then if we want to talk about rates, we can use the offset or unit conversion to convert it to a rate implicitly. I do think that, again, I don't have a great principled answer for why to use an offset instead of just do a unit conversion later. I do have a principled answer for why not to use a normal, right? And that's that the normal, the log will include some of that skewness, but it's going to still be inefficient relative to the Poisson on modeling count. So like the log normal, and it also doesn't model zeros, right? If we're using something like the log normal.
Oh, right. Yeah, that's true.
The gamma is also one that people will use, but it has a slightly different shape than the Poisson. I mean, it's not an exact science when we're making some of these modeling choices. I think we can go back to McElrath's maximum entropy principles if we do want like a definitive answer on kind of what's the least informative distribution that the constraints of the data. Then Poisson for counts with a large n and a small p is it, right?
Okay.
But yeah. You always have a lot of flexibility in these things. I think the point, and I'm glad you all are asking these questions because it shows you understand what the hell is going on here. That's great. And I guess, the typical answer in applied stats is to simulate it and see what happens, right? So if you really want to push this further, you could run a simulation where you draw random Poisson variables with an offset in how the data generating process is working, and then look at what different kinds of models give you in terms of reverse engineering to obtain the original distribution, right? That's kind of how applied statisticians often solve these kind of problems, to figure out if there's a bias in a particular procedure. It's just to simulate it and to see if we know the exact data generating process, right? Because we defined it as like an R Poisson, right? Then can we model it in a way that recovers that data generating process?
And is this when you model out of the priors to see if you can regenerate your data?
Similar. I mean, that's prior simulation. It's a similar exercise. Yeah. I'm not going to go through it, but I think you could justify either choice. The offset is such an easy thing to do that I don't think there's a reason not to do it. And it's built into, if you're using frequentist models, it's built into it. And in Ulam, it's as simple as adding that log pop in, right? And that way you don't forget to make the unit conversion later. The thing I will say, as opposed to here, right, each of our units now is the per capita rate in that county, right? Versus here, if we went and divided this by the average population size, we would get different inferences, right? Because the average for the nation is going to be quite different than if we include the rate for each county, right? Anyway, but it sounds like we're good on what the offset does. Yeah? Okay. Everyone, I feel like the questions you're asking are exactly right for understanding what the offset is doing. Yeah, and again, I'm sorry I can't give you a more definitive answer on when to just do unit conversion the way you might typically do it versus when to use the offset. Yeah, I mean, my motivation for this is I see I see smart statisticians doing it this way when they run Poisson models, and so I'm like, okay, Andrew Gelman says to do it this way, I'm going to do it this way. And McElrath says to do it this way, I'm going to do it this way, and assume that there's a good logic behind it, right? There's some kind of like expertise trust going on my end. I haven't, because I haven't actually run the simulations to see what it would do differently. But yeah. But relative to other unbounded Poisson models, which you might see sometimes, they sometimes won't include these offset terms, and now that's something you know that you can do. Okay. So let's check so now another thing that is nice for this, rather than kind of treating it in a unit conversion sense of dividing this by 100,000 later, what we can do is we can directly simulate, right? Because log population is in our model. So what I want to do is I want to simulate the number of expected deaths for African Americans, Latinos, and whites when population size is 100,000, right? So I'm going to set my log pop variable equal to the logarithm of 100,000. Then I'm going to use the link function with my FE Poisson offset model in this simulation data, convert it to a data frame, rename it, and do the pivot longer trick I did a little while ago, right? And here's what we get, right? So now I can just use sim and link when I have the offset in the model to just directly pull those from the model. So now I get the expected deaths for a population of 100,000, which it turns out is the scale I want to be on, deaths per 100,000, right? So I get an expected death count for African Americans of about 13 in a county with 100,000 population. I get an expected death count for Latinos of about 7 for a county population of 100,000, and an expected death count for whites of about 3, right? So before, right, without the offset, we saw there's more white deaths than anyone else. With the offset, we see that the rate of death for Latinos and whites is much higher. Latinos and blacks is much higher than the rate of death for whites, right? So that offset is critical to inference in this case. Now, however we want to approach that problem. Any questions?
I have a technical question previously when you were setting up the data frame, and I must not be remembering something right, but I'm seeing here that we've got 2 columns in that data frame, log pop and race ethnicity.
Yep.
And you've got 3 values in one and 1 value in the other.
Yeah. So if it's a continuous, if you only provide a data frame with 1 value, it's going to just repeat it all the way down.
Okay, because that's when I was trying to set up data frames, I was getting stuck on that conceptually. So it will just fill it in for each one of them?
Yep.
Okay, thank you.
Value, it'll fill it in the whole way. And if you give it 2, if it has an even number, it'll repeat the 2. It'll implicitly repeat. I should be explicit and say repeat 3 times, but it'll do it implicitly.
All right, great.
Yeah.
That's where I was getting stuck. All right, thanks.
Yeah, no problem. Other questions? This is great. I feel like you all have a pretty strong handle on what's going on here. So that's great. Okay, but notice that same behavior with the Poisson again, right? Very peaked on white expected death counts because the mean and variance are linked. So if the mean is low, the variance is low. And so we get a really tall peak on this guy. On this one, right? And as we go, the kind of distribution gets smushed. The tails get more spread out. The peak goes down. Now, this is not always desirable, right? There's a phenomenon called over-dispersion, where a lot of times the variance actually increases faster than the mean. So here, we're increasing the spread as the mean increases, but for most phenomenon, the spread actually increases more faster as the as the expected value increases than just that rate, right? It's actually greater than 1, right? So the variance is greater than the mean in a lot of contexts, where we're going to need an additional parameter. We're going to get into that when we talk about mixture models next week. And sometimes you might have heard of the negative binomial model or quasi-Poisson model. That's what we'll get to next time. These estimates are actually going to be kind of too liberal with our uncertainty in terms of where those parameter estimates are. These should actually be wider, right? These densities should be wider. But we'll figure out how to fix that next time. Poisson is great as a count model. It's a great tool to have in your belt. We're going to push it a step further to make sure that we're getting the variance right next time. Okay, so we're going to get into categorical regression. Anyone say yes in the chat if you need a break, or just unmute yourself and say yes if you need a break.
I think 5 minutes would be. I have.
Oh yeah. Okay. I'm going to give you 3 minutes. So let's. I've got 11:05 here. Let's come back at 11:08, just because I got babies out there that want me to come back out. All right, 3 minutes. Pause recording. So we're gonna keep going with categorical regression. Now I'm going to diverge a bit from the book's approach here. If you followed along with the reading, you'll note that McElrath uses Stan directly to code his categorical models, and that's fine. I'm going to use a new package to do that. That I'm going to kind of spoiler alert, right? I told you at the end of the semester I was going to show you some easier ways to estimate Bayesian models. I'm going to go ahead and show you that package today, just as a preview. And the last lecture is going to be fully dedicated to showing you how to use these other tools, right? And these other tools are super easy to use, with the downside that you don't have to show as much of your work, right? So if you can use Ulam well, then you can use all these other tools well, and you'll really understand what goes into the models you're fitting. If I just showed you this right out the gate, you wouldn't necessarily understand the relationship between priors and outcomes as well. You wouldn't understand link functions as well, right? So there's a reason, a method to this, but we'll get there. All right, categorical regression, right? So categorical data, but we've seen binary data. Binary data, right, is implicitly categorical, where it takes on a value of true or false, right, or one of two categories. Lots of things fall into binaries. But categorical data falls into a fixed set of categories, right? We often describe this as K categories. So it could be, more than one, more than two choices, right? So it could be unordered, meaning that there's no inherent ranking of the categories, or it could be ordered, right? And ordered categorical data has some explicit hierarchical ranking of values, right? So we might think of, for example, like school grade as being an ordered categorical variable. We might think of, many of you have maybe worked with public opinion data, right? And have seen like Likert scales, where we would range from like strongly disagree to strongly agree. And so those are ordered, right? But they're categorical. There's not like a -3, -2, -1, 0, 1, 2, 3. As many of you, and any of you have gotten course evals, and they're like, oh, well, your average is a 4.2. But is like the difference between agree and strongly agree really one? And it's the difference between agree, disagree and agree. I don't know. We're kind of, by converting them to numeric, we're putting a distance of 1 between each of them and saying that distance is equivalent, but that might not be the case, right? And we could say that the distance, like people might perceive that, like when you're driving in an Uber, right, and you get out and you give someone the 5 stars, right, we know that if you give someone 2 stars, you might get them fired, right? And so we know that the gap between like that 5 and that 4 is a lot smaller than the gap between the 4 and the 3, right? Hey, Dorothy's having fun. Sorry. Hey, come here. Do you need a hug? Sorry. You want to sit with me for a sec while I teach? Okay. Hi. I think she's scared of a cartoon. Sorry. This happens about 4 or 5 times a day. So can everyone hear me? Yeah, okay. Okay, cool. So categorical data. Yeah, categorical data. Teaching from home is awesome. Okay, so just, is candidate choice in a primary election ordered or unordered, right? That's unordered. Zip code of people choosing a place to move, right? That's a categorical outcome, the 10,000 or whatever zip codes, right? That's a categorical variable. Candidate choice is a categorical variable. Cause of death is a categorical variable, right? Opinions on a political issue on a thermometer. Obviously, we just said that's ordered. A graduate program to attend. Well, I mean, like criminal justice is way cooler than evolutionary biology, but so those are obviously unordered. But rankings are ordered, right? And is the gap between like 1 and 2 the same as a gap between 15 and 16? Maybe not. Okay, so I'm going to use the iris data to do some examples, some worked examples today. This is built into R. You can load it just using data iris. And what it is it's a data set of like 50 observations or 150 observations of various characteristics of 3 species of iris flower, right? So here we're going to say that we have we have one categorical variable, and that's species, and we have a few continuous variables. And I want to show you how we might do data visuals with categorical variables, right? So one way is to use facets. So here I'm going to do a histogram of the petal length of the, let me just show you this data. I'm sorry, I thought I had a slide that actually showed you the data. Oops, share, stop sharing, share our studio, boom. Okay, so data iris, head, iris, right? This is the data. We have 150 rows. We have these 2 sepal length and sepal width variables. Petal length and petal width are the 2 other continuous variables. So we have 2 measures of the sepal and 2 measures of the petal, and then we have a species indicator, right? So this is the data. What we're going to do is think about whether we can infer the species of a flower based on one of the continuous measures from the data. So we're going to ask whether we can predict out what species it is by looking at the width of the petal of the flower, right? So pretty trivial classification challenge, but this is something that you might encounter relatively frequently. It's a challenge like it's implicitly like the challenge of, in the case of criminal justice, a lot of the algorithms for determining fitness for community supervision or pretrial release, right? That are making all these kind of black box decisions about who gets to go free after charge, who goes to jail after charge. These are classifiers, right? These are often just logistic regression models or categorical regression models that use some features of the person that are observed to try and infer something that's unobserved. Are you going to commit a violent crime in the community? Are you going to reoffend in some way, right? And we don't necessarily know that, but we might know, for example, their income, their housing stability, their priors, stuff like that. We can put that all into a model and predict out, are you going to reoffend? Now, the classification performance there, as I mentioned, right, a false positive and a false negative can be really costly, right? So like these classifiers don't perform very well. I think they have like an 80% or something success rate. So we end up locking up a lot more people that need to be locked up. But implicitly, what these people are assuming is that it's safer to lock up more people rather than to risk that false negative, where we classify someone as not a risk, but then we release them and they go do something in the community that's politically damaging to us, right? So like the costs of incarcerating people are factored as being, less costly than the political cost of the company if they classify something wrong, because the lives of people we lock up are basically worth nothing to our society, right? So there's like a lot of things we can think about in terms of how the economics of this stuff works based on classification performance. All that is to say is this stuff is like sounds boring and technical, but it's actually like at the center of a lot of the things that are going on in our field right now.
Right.
Yeah.
I'm not seeing how is the things like petal length and everything. How are those categorical?
They're not. They're continuous.
Yeah. Okay.
Species is categorical.
Okay.
Yep. So when we visualize categoricals, right? If we're visualizing, so let's just kind of switch back. Stop sharing.
And in these models where you said to identify, this is basically going to be species morpho-species identification.
We're going to basically use a continuous measure to predict what species of flower we're looking at.
So we'll use 1 or 2 of these measures and do a morpho-species categories.
Right. Our outcome will be species.
Okay.
Yeah, I'll show you that in a sec. But I just wanted to kind of walk you through how we would visualize this stuff. So if we had 2 categorical measures, honestly, like a crosstab or a bar plot is the way to go. If we want to visualize a continuous measure across a categorical variable, facets are great. If we want to visualize 2 continuous measures across a categorical variable, then a scatter plot with color is great, right? Here we have petal length and petal width. And we can see that those 2 measures are highly correlated with each other. But then you can see that the species is now color-coded. So we can see these versicolors are all in the middle. These setosas are all down low with small petals, and the virginicas are high with large petals. Yeah? So this is a really effective visual, right? 2 continuous, 1 categorical. This works well too, and it shows us something similar with 2 continuous categoricals. 2 continuous, 1 continuous, 1 categorical. The other thing that this plot shows us is that clustering must work fine on this data, absolutely, right? For those of you who are thinking about, kind of machine learning-y type applications, clustering, there's a ton of clustering here, and we could use like a k-means algorithm to really quickly pull out the species of the data. We could use, a variety of clustering methods to pull out the species of the flowers really easily based on these continuous outcomes. But we're going to use a regression approach rather than a clustering approach to do something similar, right?
Is there like a statistical term for the fact, like if I go between the one dimension with the bar plots to this scatter plot you have, you see that the certainty of the fact that you're on the right species is really, really much higher once you've added another dimension. Is there a term for it that you're, because here you see how there's some overlap, and like if I had a value and then
I actually don't. So I was going to suggest that I don't think we actually gain much information by including both variables because they're highly correlated with each other, right? If we know petal length, we know with some degree of certainty petal width, right? And if we know petal width, we know with some degree of certainty petal length. These are correlated like 0.98. I don't know that there's a statistical term for it other than, if we were to think about it in terms of the information criteria, right? So if we were to use like WAIC in a regression context, we would see an improved model fit, right? So we would say the model fits better in a regression context by, that our residual, our predictive uncertainty decreases when we have that extra predictor in the model, something like that. Does that get after your question?
Somewhat. I mean, I see like if I look at the combination of 2 values here, my chances of falling in a place that's ambiguous between the green and the
It's still
blue is much smaller than if I go and I look at the ambiguous value between just on the petal length.
You're looking at these tail overlaps, and that's similar. So we're going to look at this in the context of regression in a second. Yeah, sure. I mean, so if like adding the extra predictor helps explain some of that uncertainty in classification, then it improves model fit, it improves predictive performance. That's how I would talk about it, right? But let's kind of keep pushing on with this. But color is a really nice way, or you could use like a shape. If they could be triangle, stars, and circles. Color, is a little easier to pull out, and there are colorblind friendly palettes you can use as well. But yeah, I really like using color for categoricals. So our research question here is, can we successfully classify the species of iris we're looking at based on the observed length of the petals, right? And I'm going to choose to only include one predictor here, observing that these are really that length and width are really highly correlated with each other, right? The correlation is over 0.9. So we don't gain much additional information by putting that other predictor in the model. So we're going to use a multinomial regression, right? So we're going to now use the multinomial distribution. You'll sometimes hear this referred to as categorical regression. Categoricals are a special case of the multinomial. Technically, the binomial is a special case of the multinomial, right? These are really closely related to each other. But implicitly, it's really similar to running k-1 logistic regression. Effectively, what we're going to do is we're going to run a logistic regression model for each of the species except for one, and the other one is the kind of held out category that's implied by the others. So what we're going to ask implicitly is, if we know petal width, what's the probability that a species is setosa rather than virginica? And if we know petal width, what's the probability that a species is versicolor rather than virginica, right? Where the probability that the species is virginica is 1 minus the probability that it's either setosa or versicolor, right? If we estimate the 2 models, we don't need the third. It's implied, right? So we're going to estimate k-1 logistic regressions. That's kind of what's going on under the hood. It's not exactly what's happening, but if you can kind of get your head around the logistic regression model, the multinomial is effectively adding additional logistic regressions in where we have actual distinct linear regression models going on under the hood. And McElrath's example kind of walks you through how you can actually specify different regression specifications for each level of the model if you want to. If you think, for example, maybe we weren't looking at flower species, maybe we were looking at like, do you like Pepsi, Coke, or ginger ale or something, right? Like maybe we were looking at like some kind of preference set. And maybe we think that like there's multiple predictors in there. Maybe like age is important, but maybe like region of the country is important, but maybe it matters for one soda more than another. We could specify, different linear predictors for each level of the outcome, right? We're not going to do that today, but we can get really complicated with these models if we want to. Because we're estimating those k-1 logistic regressions, we can also specify unique linear predictors for each of those models, right? So under the hood here, we're going to run it as if it were a single model, but it's actually running multiple models. Yeah? That sounds confusing. It's confusing, right? So for the categorical outcome with k categories, we're going to let 1, 2, 3 stand in for group membership 1, 2, 3. Effectively, we're estimating the log probability that y is in group 1 over y is in group k, y is in group 2, y is in group k, y is in group k-1, y is in group k, where y being in group k is held out, and everything is in reference to that, right? So everything is in reference to the log odds of being in group 1 through k-1 over k, but k is left out, right? In the binary context, we model the probability that the event is equal to true, but we don't model the probability that the event is not true, because that's implied, because it's 1 minus, right? The probability in a binary context of, so if we have a Bernoulli variable, right, it has one parameter, which is a special binomial, right? We have one parameter p. So the probability that the event happens is p. We don't need to estimate the probability that the event does not happen because it's defined to be 1 minus p, right? So if we estimate the probability that it's in group 1 to up to k-1, we've actually estimated the probability it's in group k by 1 minus the sum of the probability it's in the other group. Does this make sense? Anyone have any questions about how this works? The mechanics are complicated, but this is going to be another one where I don't want you to look at the regression output directly, right? Because these models are really messy, right? But working on the predicted outcome scale, fine. And I'll show you how that looks in a second. The key assumption here is the independence of irrelevant alternatives. So the odds of the choice can't depend on the presence or absence of other alternatives, right? So like my choosing to ride a car or a bus depends on the presence or absence of a bus, right? If I'm in a place that doesn't have buses, then I can't choose to ride a bus. And if the buses are really good, then I might choose to use my car less often, right? So here we need to think that the kind of choice set doesn't depend on one choice being there or not being there. Don't worry too much about that assumption. So like a red bus versus a blue bus might not affect our choice set very much, but car versus bus, if the bus is not present, might, right? If I don't care about the color of the bus, then that might. Don't worry too much about this assumption if it doesn't make sense, but that's kind of the assumption that goes into the multinomial model that's unspoken. So again, the book provides details on using Stan. Using Ulam to do this is possible, but it's undocumented in McElrath's book. And I looked for some documentation for how to do it and couldn't find any. So I was like, okay, cool, I'm going to use BRMS. So BRMS is a software package that takes the syntax from R's base modeling functions like LM and GLM, and also uses the syntax from a really great multi-level modeling package called LME4. That's the kind of standard way to estimate multi-level models from a frequentist standpoint in R. It basically takes that syntax and applies it to Stan. And so it's a Bayesian package that lets us estimate Bayesian models using Stan and using the same samplers we've been using, but we can write the models in a little bit more of a compact way. So I'm going to cheat and use that. This is what I'm going to show you at the end of the semester. So,
quick question about, so you said we're making this assumption for the multinomial, and basically if we find that we can't make that assumption, then we should be using something else?
yes.
Okay.
Yes. You should use something else if you have reason to believe that the alternatives are not irrelevant. Yeah. So yeah, that I think is a good good approach. Is yeah, I and categorical models get really complicated really quickly. But yeah, there's a lot of literature on categorical classification models that you could dive into there. Okay, so BRMS. If you have RStan working, you can install packages BRMS now, and this will work fine. It's going to choose sensible priors. It's going to choose weakly informative priors automatically. And so this is all I need to run the categorical model in BRMS, right? And if you run this, you'll see that it goes through the same sampler output that you get using Ulam. So if this looks a lot nicer than what we've seen using the Ulam models, we'll eventually get to a point where we're doing everything in this way, right? And this is far easier, but it's also hiding a lot, right? It's hiding a whole lot. So you need to understand what the models are doing before you use these kind of higher level tools. But again, I'm cheating because I couldn't figure out how to do it with Ulam. Okay, here's the model output. It looks pretty similar to what we get with Ulam, right? We have our MAP estimate, we have our variance on that estimate, and we have confidence intervals on it. We also get that R hat we get from Stan, and we get the effective sample size, and this is just averaged over each chain, right? And those ESS and R hats look fine to me. Now, anyone want to try and interpret these parameters? The log odds of being versicolor versus virginica relative to petal length. And here, what's the held out category? It's setosa, right? Like this is totally uninterpretable. Just looking at these parameters, right? The log odds of being setosa rather than versicolor when petal length is 0 is minus 39, right? The log odds increase by 14.5 of being versicolor rather than setosa for every 1 unit increase in petal length, right? This is just like, you don't interpret these from a parameter table, right? Just don't do it. But check it out. This is great, right? So the conditional effects plot basically asks, as we move petal length from its minimum to its maximum, this is exactly the same as the kind of, if we set up the counterfactual, petal length goes from 0 to 7, where do we classify the flower, right? This just kind of is a baked-in way to do it in the BRMS package. What do we see? We see that if petal length is very low, we are almost certain that it's a setosa, or we are certain that it's a setosa. The probability is 1, right? But as petal length gets to around, let's say, 2.5, we still think it could be a setosa, but there's some probability that it could be versicolor, right? And then once we're in the sort of like 3 to 5 range, we're certain it's a versicolor. But, there is this middle range where we have some uncertainty about which flower it is, right? In that range of about 5, right? Which, looks pretty similar to what we saw here on our scatter plot, right? What this is telling us is if we observe a flower with a petal length of 4, the model says it's definitely a versicolor, right? If we observe a flower with a petal length of 6, the model says it's definitely virginica. If we observe a flower with, a petal length of 2, the model says it's definitely a setosa. If we observe petal length 5, right, the model says, okay, you've got a 75% probability it's virginica. If you observe it at 5, you've got a 25% probability it's a versicolor, right? So if we're using the 0.5 classifier rule, then we're going to say, yeah, that's a virginica, but we're going to be wrong sometimes, right? And so that's a trade-off we need to think about whether we're willing to make. In this case, it's pretty costless, but if it were, a more consequential thing, then it might not be costless. So this is how I strongly suggest you interpret categorical models, is on the scale of the probability of the outcome, right? Don't look at this. I mean, look at it to check convergence, look at it to see if there's something funky going on with your model. But unlike, I've been hammering this all semester, but this is a context where you absolutely cannot make interpretations based on the parameter table. It's too confusing, right? Because you have the held out category, because you're on a log odds scale, which is weird anyway, right? You have to make interpretations on the scale of the expected outcome, which is the probability that it belongs to a particular group, the probability of the choice, the classification, right? This is the scale we have to look at it on. Okay, so that's it for categorical models that I've got for you today. Any questions? This is a pretty brief treatment of them. This is obviously a really vast kind of field of research. Yeah.
So the errors are just in like the width of like the
Errors are just a reflection of our uncertainty of the posterior of that parameter of the intersection.
I'm talking about in the graph. That.
Those reflect the parameter uncertainty, right?
Yeah.
So that's
yeah.
posterior
Okay.
uncertainty, but it's now on the scale of the outcome. And so remember the logistic function, right, is nonlinear. And when it gets up close to 1, differences between like 0.99 and 0.999 are really small. And so that's why they down to 0 and then widen as they get closer to the midpoint, because a jump of between 0.5 and 5.51 is a big jump on the scale of logit, right? But a jump on on the probability scale, moving from 0.5 to 0.51 is a larger jump on the scale of Victor than is moving from 0.99 to 0.999.
I guess I'm sort of confused because I would assume that the Virginia and Versicolor, since they have some overlap, that the band would be larger there than the Setosa versus the Versicolor, but maybe I'm
that's
just making assumptions.
That's a good question, and we could do some more simulation to think about exactly what's going on there.
Okay.
Yeah, no, I mean that's a good observation, because we do have a little more certainty that there's a gap between those two based on the scatter plots, right? Yeah, I can't tell you exactly what's going on there. We don't have a ton of data, but yeah, I don't know exactly what's going on.
If we had just trying to wrap my head around this and all that. So if you had a different variable other than petal length, because that's continuous in nature, 0 to whenever, is there an alternate way? Like, I don't know. I'm just trying to think of, like, let's say this data set had flower death, like that. This wouldn't work. I'm just trying to.
Oracle predictor? Sure, it would.
Yes. Oh, okay.
You can add that in to our model. Right here, we just have petal length. So imagine this is implicitly A plus B times petal length, right? I'm just typing the formula into the chat. There's no reason we couldn't do A plus A time, A bracket flower death bracket plus B times petal length, right? There's no reason we couldn't fit multiple intercepts, right?
Okay.
For a categorical variable. And we could have like 4 categorical variables, and then we have different intercepts for each level of those categoricals. We're going to get there when we get to multi-level models too. And ways to fit that. But yeah, no problem at all with that. If you have enough data and you have theoretical motivation to include it in the model, no problem.
Okay, thank you.
Yeah. Okay. So we added 2 new likelihoods into our GLM tool belt today, the Poisson and the multinomial, right? These are flexible and powerful regression models. And you should basically be thinking of GLMs as sort of like, okay, now when I see new kinds of data, I have new regressions that I can use to model these kinds of data. But I can still use everything I already knew about the linear regression model to fit those models, right? I can use interactions, I can use DAGs, I can use all that stuff because I still have a linear predictor, right? But the difference is, again, that that link function and some of the assumptions in the model often make interpreting things directly on the parameter scale hard. And so working on the outcome scale with visuals is really critical. Poisson regression handles counts and rates easily. Multinomial regression models categorical outcomes and handles classification, right? And there are many other approaches to classification that if that's a topic that is important to your research, there's a ton happening on classification out in the world right now, both in kind of applied stats and in data science. So for homework, again, optional, but if you want some practice with this stuff, I'm suggesting the easy and medium questions from chapter 11 as good practice for both logistic regression models and Poisson and multinomial models. And if you want practice with the Poisson models, add in the hard 4 question, the 11H4 question. It's on salamander population sizes in forests, right, where you're looking at counts of salamanders based on various characteristics of forests. The book, just remember that when you see map or map to stan in the book, those are the same as QUAP and ULAM, right? That's just the version 1 versus the version 2 of the software. So without, take a few minutes for questions. Seems like we might have already addressed them kind of going through, but I believe we have 5 lectures left after today. Next time we're going to get to mixture models. So we're going to get to times when we combine multiple likelihoods into the same model. So we might have, in the case of the over-dispersed outcome, we might have kind of 2 random variable processes going on at the same time. We're also going to cover zero inflated outcomes, right, where we might have an account approach. We might have one feature of the data determining whether the event occurs at all, and another Poisson feature determining how many times the event occurs. So those are neat and pretty broadly useful. Then we're going to get into multi-level models. We're going to spend 2 weeks on multi-level models, a week on missing data, and then we're going to get to using the kind of easy, tidy sort of packages to use Bayesian models. So we're getting close to the end. But yeah, any questions? No? Okay. Enjoy the rest of your day. And yeah, I'll see you on Slack if nothing else. Stay safe, stay well.